Now let us take an example of a TS diagram and see how to study it. So this is here entropy plotted and here I have plotted temperature. So we have a process like this. This is temperature T naught and this place the temperature T naught by N. Now let us see what is the efficiency of this process A, B, C. So let us calculate the efficiency for the process. Now let us, in order to calculate the efficiency, we have to see each and individual processes. Suppose I say this is S2 entropy and here I have S1. Then consider the process A to B. Now A to B process, the temperature is constant, that means it is isothermal process. So let us see what is the heat intake in the system. The entropy increases, temperature is constant and entropy increases, that means heat comes, Q1 amount of heat enters into the system and that Q1 will be given by the area under this curve. So Q1 amount of heat enters, that is given by area under the curve, that is Q1 is equal to, that is area is T naught into S2 minus S1. This is the total heat coming from this. Now come to B to C. Consider the process B to C. Now B to C, the entropy does not change. There is no change in entropy in the system. So you see, you recall delta S is equal to delta Q by T. So since this is 0, so delta Q is 0. So there is no heat intake. So the process is adiabatic because S2 does not changes. Next, consider the process C2A. Now C2A process, the entropy is decreasing and so heat is going out of the system. So heat going out in the system is the area under this curve, that is this trapezium, that is given by half into this S2 minus S1 into sum of this T naught plus T naught by N. So this is minus because this heat goes out of the system. So this is the heat going out of the system. So let us not write it because already I have shown is the heat rejected to the sink, I can say, because this is lower temperature, higher temperature. If I denote this as an engine, then you can see something T naught here and we have seen this is T naught by N, this is sink and this is source. So it takes Q1 amount of heat, gives Q2 amount of heat and does some work equal to Q1 minus Q2. So now we wish to calculate the efficiency of this engine. So efficiency of the cycle is equal to, we will see this is work by Q input and this is Q input minus Q2 by Q1, that is 1 minus Q2 by Q1. So this efficiency is equal to 1 minus theta 2 is this quantity, half S2 minus S1 into T naught N plus 1 by N upon theta Q1, that is T naught S2 minus S1. So this term cancels out this becomes 1 minus n plus 1 by 2n, that is 2n minus n minus 1 by 2n, that is equal to n minus 1 by 2n. So thus efficiency becomes n minus 1 by 2n for this cyclic process. This is how we work in TS diagram. So we have earlier seen PV diagrams and calculation of efficiency in PV diagram, and now we will see TS diagram. So let us take one more example. So now let us take another example of TS diagram. This is S, T plotted here, and this is your S2 here. Suppose S2 S1 is not given, I have assumed it. So this is not given, I will assume it. So what is the given quantities? This is T0 and T0 by N. It goes from A to B, B to C, and C to A. So now let us assume why we have to find the efficiency of this cycle. I will assume this as S2 and this as S1. So consider now the process, consider the process A to B. Now you see A to B, the entropy is increasing and the temperature is decreasing. So what is happening? If entropy is increasing, that can only happen at the cost of delta Q. So you see ds is equal to dq r by t. So if ds is increasing, if entropy is increasing, there must be heat inside the system. That means heat is entering in the system as Q1. So the amount of Q1 that enters into the system is given by the area under the curve, TS curve. So that is how much this area. So this area is half, then this difference S2 minus S1, and then T0 plus T0 by N. So that is half, this is T0 by 2, S2 minus S1, N plus 1 by N. Next, consider the process B to C. Now B to C, when I come, the entropy is decreasing and so heat is rejected out of the system. Rejected heat is Q2. So the heat is rejected to the sink at temperature T0 by N. So how much is heat rejected? Q2 is equal to, that is again the area under this curve, that is T0 by N into S2 minus S1. Again C to A, the entropy does not change, means it's an adiabatic process, nothing happens. So the final thing is that this is the source at a temperature here, and we have a sink at a temperature T0 by N, and it takes Q1 amount of heat, converts into work, and some amount of heat Q2 is rejected. So again we define efficiency of the engine as work by Q input, that is Q input by this 1 minus Q2 by Q1, that is 1 minus Q2 is this T0 and S2 minus S1 upon Q1 input is this much, that is T0 by 2 S2 minus S1 N plus 1 by N. This cancels out. Efficiency is equal to 1 minus this 1 by N cancels out. 1 by 2 goes this way, 2 by N plus 1, that is equal to N plus 1 minus 2, that is N minus 1 by N plus 1. So we have efficiency of this process as N minus 1 by N plus 1. So let us take an example. We have already seen this example previously. 2 moles of an ideal gas are cooled isochorically and then expanded isobarically to bring gas to the initial value. Find the entropy increment of the gas if in this process the gas pressure changed n times. So, initial value, so here temperature. So, let us see that in order to get the initial value of the temperature, what we have to do. So, now you see this is our PV diagram. Let us first use PV diagram to understand what we are talking. So, we have 2 moles, certain moles of an ideal gas. Suppose the ideal gas is here, it is cooled isochorically. So, isochorically means we have cooled it. So, it comes down like this, and then expanded isobarically expanded here, so that the gas goes to the initial value temperature. That means the initial temperature and this point, these 2 points are on an isotherm. So, it is an isotherm. So, these points, initial point and the final point lies on the isotherm. So, find the entropy increment of the gas if in this process the gas pressure changed n times. So, this is suppose P naught, this is P naught, let this be P naught, so it will become N P naught. So, previously it was N P naught, now it is P naught. So, we have to calculate the entropy change during from here to here. Now, we know that if I go from this process or this process, the entropy change is the same because entropy is a state function. So, since entropy is a state function, so its change along the isotherm from I to F will be the same as along the given isochoric plus isobaric processes. So, what we get from here, we will also get from here. So, better to calculate this process delta S for this process. So, let us see what is delta S for this process. So, we have delta S as dq reversible by T for an isothermal process, for an isotherm. So, this we are going to calculate for an isotherm. Let us recall delta Q is equal to delta U plus delta W for that isotherm, and for an isotherm delta U is 0 because for an ideal gas delta U, if there is no change in temperature, delta U is 0 and dW is equal to PdV by T. Now, PdV by T, P is equal to nu R T, P is equal to nu R T by V dV. So, this cancels out, we will have nu R dV by V. So, that is again equal to nu R, this ln, this dV by V is ln V2 by V1, this is, that is V final by V initial. So, now delta S we got nu, that was 2 actually given, R and ln V2, this is V2 V final and this is V initial, you can say. So, here V is equal to suppose nu R T naught by this here pressure. So, this volume V is equal to this nu R T by pressure, that is P naught, this is V2, and here V1 volume will be equal to nu R T naught by N P naught. So, we have V2 this by V1. So, this quantity divided by this will be here nu R T naught by P naught upon nu R T naught by N P naught. So, this is nu R ln, this is N. So, thus implies the final result is nu number of moles R ln, that is log n. So, this is what the increment in delta S that you can calculate from here or here, both are going to be same because entropy is a state function.